Okay, Mr. Mondopu Moisen Mulawasa. Niko Mulawasa.
What a for. Papa, babligo na banjensha zone na chika da pana chika library. At banjensha na kurumu ku kontak in the folk ya cha de kare son. Again, you feel cha zone. Cha chinka ika.
No, no, welcome, welcome, welcome. Um, this is linear algebra, right? So we're doing linear algebra.
Yes.
Right. So for the second one, the second question here, that's us to determine whether S is a what is a.
You're not sharing your screen.
Oh, you're unable to see my screen. Just a minute. Okay, are you able to see my screen now?
Yes, I'm able to see your screen.
All right, so we're talking about the first question, which is which is this one. So we've been given a set that has T, and T is an element of the vector space, and T has a definition that T of 0 gives you 0. Determine whether S, which is the entire set, is a subspace or not. Are you able to see that?
Yes, I'm able to.
All right, let me just switch to my whiteboard. All right, so if you see this question is about subspaces. Okay, so now the general idea between or
Yes.
around subspaces is that we will be given a definition. So like in this case, this is a definition. Okay, then we'll be checking if this definition is a subspace or not. So we'll be disproving if the definition given is a subspace or not. Now, for us to disprove whether a subset is or not, it has to be closed under addition and closed under multiplication. Closed under addition simply means that if you get two vectors from the given definition. So in this case, if we get two vectors from this definition, which is S, and we add them, if we add them, what we should get is the same definition. So the addition of these vectors should also be part of the definition.
Which is 0.
No, as in they should maintain the definition.
Okay, okay.
Yeah, I'll give an example before we do this one, right? So that is the first one. So if you get two vectors in the given definition, when you add them, they should maintain the definition. That's the first one.
Yeah.
So then the second one, if you get one vector from the definition and a scalar from the K space, when you multiply the vector and the scalar, they should maintain the same definition. Are you getting this?
Yes.
Yes. So these two conditions have to be satisfied. These two conditions, all of them should be satisfied. Okay. So the first one is if you get two vectors from the given definition, you add them, they should maintain the definition. Secondly, if you get a vector from the definition and you multiply it with a scalar from a K space. So a K space is basically where we get scalars. This is where scalars stay. And you multiply that scalar with the vector from the definition, they should also maintain the what? The definition. They should be part of the definition. Let me give an example. Yeah. So let me give an example of a case where one will maintain the definition and another one will not maintain the definition, right? So suppose if u, or let's say if v, or give this, if v is defined by u equals to let's say 0 comma a comma b comma c, where u is an element of v, is this a subspace? Okay, so we have that question there. So v is defined by this, meaning that all vectors in v will be defined by this. So we're going to let two vectors. So we're going to try the first one. So this one, addition, is called closed under addition. The first one is called closed under addition. Okay. Then the second one is called closed under multiplication.
Multiplication.
Yeah. So now we are going to let two vectors u comma v be elements of the given vector, which is capital V. Now, if these vectors are elements of the capital V, then u will have a 0, should have a 0 there. Then here they can be any other letters. Alpha 1, alpha 2. This is a 4-dimensional vector. 1, 2, 3, 4. Alpha 3. Meaning that V will also have the same definition because it belongs in this space, which is 0. Then here there can be any other scalars, b1 comma beta 2 or b2 comma beta 3. Okay, now if we add these two, u plus v, are they going to maintain this definition? So that is what we are asking ourselves. So we add, we see that we're going to have this plus 0, it will just be 0, right? Comma, this plus this, that will be alpha 1 plus beta 1, comma.
So when making this method, elements, we need to follow what is inside. Okay?
Yes, that's why we've said here, we've said that we let u and v be elements of the given definition. So if they are elements of the given definition, they go with the property of the given definition. They will be defined like the elements in the given definition. So like in this case, u and v are elements of in the given definition. Then they'll be defined by this. All elements in this definition have a 0 as the first entry. Then here they can be any other letter. Here they can be any other scalar. Here they can be any other scalar. So if we let these two vectors u and v be elements of this given definition, then these, they'll follow suit. U, they can have they should have a 0. It's a must that they should have a 0 here. Then here they can have any other scalars. Same applies to v. Here they can be a 0. Then here they can have any other what? Scalars. Okay, so now we are trying to see if we add these two, are they going to maintain this definition of vectors in V?
Okay.
Are you seeing that? Is it clear?
Yes, it is. It is.
Yes, so we are trying to add them. So there are just two conditions. We're going to add them and then we're going to multiply with a scalar. So adding them, we see that here we're going to have alpha 1. Here 0 plus 0, it will be 0. Here this plus this will be alpha 1, beta 1. This will be alpha 2, beta 2.
Alpha 2 plus b2.
Then here
alpha 3 plus beta 3.
All right, plus b3. Now the question you should ask yourself is, have they maintained the definition? Okay, have they maintained the definition?
No, they are all detail.
No, so you are comparing to this. Here, do you have a 0 on the first entry? Yes, we have a 0.
Yes.
Here, do we have any other scalars? Yes, we have any other scalars. Here, do we have any other scalars? Yes, we have any other scalars. Here, do we have any other scalars? Yes, we have any other scalars. So we see that when we add this, it will still maintain the definition. It will still be part of the set V. Okay, now let's try to multiply. So number 1 has been verified. So we are saying u plus v is still an element of the given space. Number 2, when we multiply, so the first one is closure under addition, then the second one is closure under multiplication. So we need to multiply alpha times a vector from the given space. So in this case, alpha times the vector, which is u, which is 0 comma alpha 1 comma alpha 2 comma alpha 3. When we multiply, what are we going to have?
Yes.
Yes, when we multiply alpha times everything here, what are we going to have?
So there we are multiplying alpha times 0, it's 0. Alpha times the alpha 1, it's alpha 1. Then alpha times the alpha 2, it's alpha 2. Alpha times alpha 3, it's alpha 3.
Okay, so now does it maintain the definition? Does it maintain the definition?
Yes, it does.
Yes, it does. And why is it maintaining the definition?
Because we are using the two properties, which is under addition and under multiplication, right?
No. So the reason why this one maintains the definition is because here you see here in the definition they're saying that elements in this definition, the first one should be what? A 0. And here we have a 0. Okay, meaning that if there was a different number here, then this one would have failed to maintain the definition, and we would have concluded that it is not a what? A subspace. So this one has maintained this definition here. So here we have a 0 in the given definition, and here when we multiply alpha times the given vector, we still have a 0 here. Here we have a 1, and here we have any other scalar a, and here we have any other scalar. Here we have a b, and here we have any other scalar. So here this one also verifies. So this one also is still an element of the vector v. Then now you can make a conclusion to say, since u plus v still remains an element of the given definition, and alpha u still remains an element of the given definition, then we say v defined by u equals to 0 comma a comma b comma c is a subspace. Now I just want you to get the idea so that when we do that one, you won't have any problems. So now I want us to look at a situation where we are not going to have a subspace. Is it clear?
Okay.
So now, and for this one, I'll just do a simple one. Okay. What I'll do is this.
Okay.
I'm just going to change the question, and instead of putting a 0 here, I'm going to put a 1. So let me erase everything else. So here, okay, where am I? All right, so let's look at this question now. Right? So now, if V is defined by U, which is this, where U is an element of V, is this a subspace? So now instead of a 0, we have a 1 there. So the definition clearly says that all vectors that are in here, they should have a what there?
A 1.
A 1. So now we're going to let U comma V be elements of the given vector, which is this one here. So now if these are elements of this given vector, what would be their definition? What would be U equal to? Can you give me what U will be equal to?
Come again.
If U and V are elements of this vector, how would they be defined as? How would they look like? So what will be on the first entry of each vector?
That one to be, we'll get 1. We can get alpha 1, alpha 2, comma alpha 3.
Very good. Because we are just following this definition. Right? So for U, it should have any vector in this space should have the first entry as a 1. Then here there can be any other what? Scalars. So meaning that V would be equal to what? V would be equals to what?
Our V, our V will be equals to 1, beta 1, beta 2, beta 3.
Very good. So now here we need to test the two conditions. So for the first one is closure under addition. So that is if we
closure
add
and closed, it is the same. Huh?
Yeah, it's closed or closure under addition. So the first one is we should add U plus V. So if we add U plus V, are they going to maintain the definition? So we'll start. Right? So what is U plus V vectors? We add according to the entries. Right? So here when we add 1 plus 1, what are we going to have?
This is 2.
2. Here
2.
we're going to have?
Then alpha 1, alpha 1, beta 1.
Then
we have alpha 2, beta 2. Then we have got alpha 3, beta 3.
Okay. Now here, I'm going to ask this question. Here, does it verify the definition here on this entry here? Just the last entry here.
So since it's alpha 3, beta 3, it is C.
Yes, so here it verifies the entry. Right?
But does it?
I was saying, does it verify the entry here? Yeah. So we are saying here there can be any other scalar. So when you add these two, it will be any other scalar and it verifies the entry there. Are you seeing that? Then here, does it verify the entry there?
Yes, it does.
Yes, it does, because here they're saying on the last, the second last entry, there can be any other scalar, and this, when we add this, it will give us any other scalar. Then here on this, does it verify the entry here?
Yes, it does for A.
Yes, it does. Then what about here? Does it verify the entry here?
Yes, mean that we need to have there now a coefficient
Here, so here does
or a
not it
constant number.
here no here it does not
It is
verify.
not the same one and it is
Uh-huh.
different.
Yes. So here, since this has failed to verify the entry, this one does not belong to this space. So we can say this one is not an element of what? Of a V, because in this V, the first entry should always be a 1. But here we have a 2. Then the second entry can be any other letter or any other scalar. Are you seeing that? So meaning that closure
Yes.
under addition has failed.
It has failed.
And once one of the closures fail, we conclude that it is not a vector space. So, I mean, it's not a subspace. So this V uh, defined by U, which is equal to 1 comma A comma B comma C is not a subspace because it fails it fails to be closed under addition. So it fails to be closed under addition.
Okay.
Okay, it fails to be closed under addition.
Yes.
Yeah, if you even tried closure under multiplication, it will still also fail. Are you seeing that? Let me say, if you let's say
This
start,
addition has failed.
yeah.
Uh,
So if one
Under
of the
multiplication, I'm sure it can. Under multiplication, because when you multiply 1 times 1, it will still remain 1. So
mm-mm,
under multiplication, maybe it may pass.
mm-mm. So here, even if it passes under multiplication, as long as it fails under addition, we conclude that it is not. You get the idea?
Okay. Yes.
So sometimes it can pass under multiplication, but under addition it has failed. Or sometimes it passes under addition, but under multiplication it has what? It has failed.
Failed.
So the two conditions should be verified. So let's try, just for clarity's sake, let's try closure under multiplication. So closure under multiplication, if we get alpha times u, we're getting the vector, we're getting alpha and the vector u. What is the vector u? It has a 1 comma what? Alpha 1 comma alpha 2. When we multiply this alpha times this, it will be what?
It will be alpha.
Alpha comma alpha times that,
It
alpha.
will be alpha 1.
Yes. Then the other one,
It will be alpha 2.
yes. So you see, this one also is failing. Why is it failing?
You haven't put 3. It was supposed to be 3.
Oh yeah. Okay. Yes. Yeah.
Because it is failing because of yeah, where there's just alpha. It was supposed to be 1.
Very good. You see that, So it is failing to meet that condition there. So even closure under addition has what? Has failed. So this is alpha 3. So even closure under addition has failed. So we see that alpha u is not an element of V. Okay, because here on the first entry here, there should be 1. The definition should be maintained. So that's the idea between vector spaces and subspaces.
Okay.
Okay, now to our question. So we can now go to our question. Okay, so now our question. This is our definition. Right? Are you seeing this?
Mm.
So this is our definition. So if we do
Yes.
closure under addition and closure under multiplication, will the definition be maintained? If the definition fails to be maintained, under both conditions, we determine that S is not a subspace. Okay, so for T,
Yes.
that is an element of. Hello, Mr. Mandopo.
Hello.
Yes, so I was saying for T, that is an element of a vector. For these vectors, when you have T times 0, it should give you what? 0.
0.
Yes. So now closure under addition. Closure under addition, we're going to let U and V be elements of this set S. Okay? Are you seeing that?
Mm-hmm.
Now, if we let them to be under
Yes.
elements of set S, we're just following the same thing here. That is here. If we let them to be under the elements of set S, so here where there is T, it's the same thing as you put U element of V, then here U of V. So here U of 0 should be equal to what? 0. Are you seeing that?
0.
So same thing here.
Yes.
If we decide since V is also an element of S, when we say V here, V element of V, then V of 0 should also be equal to what? To 0.
0.
So number under closure we are just adding. So U plus V will just be equal to U of 0 plus V of 0. Okay? And what is U of 0? It is 0. And what is V of 0? It is also what? 0. So we see that this is giving us what? 0. Which maintains the definition.
0.
Okay? So which maintains the definition. So U of 0 plus V of 0 maintains the definition, which is equal to 0. So this is an element of what? Of S. Are you seeing that?
Okay.
Okay. Any questions before we
Yes.
go on?
So you like to say U open bracket 0 plus V 0 is an element of S. Okay.
Okay. So is it making sense?
We can proceed.
All right. Yes.
Yes, it
So
is.
since so for instance here, uh, closure under addition would have failed if we added U of 0 and V of 0 and it gave us maybe 5 here. So if it gave us 5, it means that it has violated the definition. It is saying when whatever vectors that are here, remember when you add vectors, you're just creating another vector. Okay?
Supposed to be 0.
Yes. So whatever vector that you have here, whether addition or what. So here, that's why you see that others, maybe they will even say U plus V then of 0, because you can factor out the 0. Then this would be like this, and this would also be equal to 0. So it's something like that, which I think I've seen from that solution that you presented.
Mm-hmm.
Yes. Now we go for closure under multiplication. Okay, so closure under multiplication, we're just getting alpha u. Okay, so if we get alpha and u, they should still maintain the what? The definition. Okay, so alpha u will be equals to alpha and u of 0. Alpha times u of 0. Okay, which would be equal to alpha times what? Alpha times what is u of 0? So what is u of 0?
It is 0.
0. And what is alpha times 0?
0.
Alpha times 0?
It is 0.
0. So we see that alpha u,
it is 0.
Yeah. So we see that alpha u also maintains the what? The condition, because it still stays in S. All right, so having that said, what would be our conclusion since closure under addition and closure under multiplication have been verified?
So they were trying to say this is also determine whether it's a subspace or not. A subspace removes the zero.
So as long as the closure under addition and closure under multiplication have been verified, the two conditions have been verified, then we can conclude whether it's a subspace or not. So if the closures have been verified, we conclude that it is what? A subspace. If the closures fail to be verified, we conclude that it is not what? A subspace. So in this case, what will be our conclusion?
So we conclude, we say therefore S is a subspace.
Very good. Can you say that again? I didn't get that.
Therefore S is a subspace under the two conditions, closed under addition and closed under multiplication.
Very good, very good. So S is a sub. Yeah, so you conclude like that. So in your conclusion, you just write this conclusion. S equal to the way it has been defined for whatever t element of V. That was t of 0 equals to 0 is a subspace. Okay, because they, or it has been verified under closure addition, because it has been verified under closures of addition and multiplication. Addition and multiplication. Okay. Yeah, so the main idea is when we use the closures, are they maintaining the definitions given? Okay, so for instance, we use closure under addition here. Was it able to maintain the definition? We're using closure under multiplication. Was it able to maintain the definition? And here we see that they were maintaining the definition, because when you multiply a vector times u, you're still getting a 0. And here we're told that if you, whatever vector should be there, it should give us what? A 0. Same applies here. If you add the vectors, you are also getting a what? A 0. So meaning that the closure under addition and multiplication have been what? Have been verified. Okay, so now we can look at linear independence.